Okay. We are going to do example one, which is the example from your book. So if any of this doesn't make sense, you can look in the book, although I think we're going to fill in some parts that the book sort of assumes you already know how to do. And I just want to make sure it's clear. So a mass weighing 2 pounds stretches a spring 6 inches. At t equals 0, the mass is released from a point, and I forgot to write it in the notes, so it should be 8 inches below the equilibrium position with an upward velocity of 4/3 feet per second. Determine the equation of motion. Okay, and so since this is an engineering problem, we need to change our systems of units. So we're going to need to change inches to feet and convert the weight of pounds to slugs. Okay. And so recall, just in general, you should already know that 12 inches is a foot and weight equals mass times acceleration due to gravity. And so if we're solving for mass, then m equals w over g, and w is in pounds. And since we're going to convert this to slugs, then we're going to use the 32 feet per second squared conversion for our acceleration due to gravity. Okay. And from this information, we know that at t equals 0, the mass is released from a point 8 inches below the equilibrium position. Now, if you go back to your notes and look below, if we're going below the equilibrium position, then that means x is going to be positive, right? So that gives us this part here, the x of 0 is 8. But then it says an upward velocity of 4/3. So in terms of thinking about this, if it's an upward velocity, then it's going in the opposite direction. So therefore, x prime of 0 is negative 4/3. So it's sort of going against where the mass is going down, right? So, but if the velocity is upward, then it's going against the mass going down, and so there's that negative 4/3. Okay, so we have that initial information, and that's really important to make sure you understand how to set that up. Then from there, we see that we can convert our everything that has inches to feet, and we're going to convert our mass. So we're going to convert from pounds to slugs. And so here, we do that on the next slide. We'll do the conversion to slugs on the next slide. But that's sort of how you set it up. This is something I remember actually doing something similar in chemistry to convert from, certain units to other units. But 8 inches, and so it's basically 8 divided by 12, right? Which is 2/3 of a foot. And then 6 inches is a half a foot, okay? We already know, because of our model, our differential equation model here, that we already know, remember, it's really this plus omega squared, right? X equals 0, okay? But I kept it as k over m because it's easier to find those elements and then put it together, right? But from that, we know it's going to have complex solutions, and so with the real term being 0, and so and the imaginary term being omega, and so that's how we get the C1 cosine of omega t plus C2 cosine sine of omega t. Okay, so again, we know that weight equals mass times g, which is acceleration due to gravity. So mass equals weight over g, and we were given that the mass weighed 2 pounds, right? And so that's where that 2 comes from, divided by 32, which is the acceleration due to gravity when we want to convert to the unit slug. So it's 1/16 of a slug. Again, that's our differential equation. We're going to use Hooke's law to figure out our k, right? So we need to find our k value. And so we're going to use Hooke's law because we already know what m. So m is 1/16, right? So we need to find our k value in order to set up our differential equation so we can solve for it. And so Hooke's law, we're going to use the one with the positive k because we're trying to find the spring constant. We're trying to find k, which represents the spring constant. And in order to do that, we were given the fact that a mass weighing 2 pounds stretches a spring 6 inches. Okay, so that's our setup is in this first sentence here. So the fourth, so it would be 2 equals k times 1/2. All right, because remember we changed. So in this case, x is representing the how far it's stretching the spring, right? The elongation. So in this case, it's 6 inches, and 6 inches we changed to feet is a half a foot. Okay, and so we have here that tells us the k is equal to 4. Okay, so now we have, and that's pound foot. Okay, and so now what we have, we can now set up our differential equation. So d squared x over dt squared plus k is 4, right? And then m is 1/16, x equals 0, and that will go to d squared x over dt squared plus what, 64? X equals 0. And if we look at the auxiliary equation, although we already know what it's going to be, but we look at this auxiliary equation, m is equal to plus or minus 8i. Okay, and so that means our x of t is c1 cosine of 8t plus c2 sine of 8t. And we know because the question gave us the initial position information as well as the velocity information. So we're going to have to find x prime of t. So let's do that now. X prime of t is going to be what? Negative 8c1 sine 8t, right? Plus 8c2 cosine 8t. Okay. And now if we substitute in, remember we're given that x of 0 equals 8 and x prime of 0 equals negative 4/3. So I want you can go ahead and pause the video and finish solving for your C1 and C2 and come back to receive your final answer. Okay, welcome back. So your final answer should have been x of t equals 2/3 cosine of 8t minus 1/6 sine of 8t. And this is our equation of motion. Okay, so hopefully that was straightforward.